Good morning. We're going to start with question number 5. Question number 5.1. Table 2 shows some enthalpy change data. So you got the enthalpy change data here, which is lattice, enthalpy, and that one is hydration and hydration. So hydration calcium ions and hydration of chloride ions. So use the data table 2 to calculate the molar enthalpy change from calcium chloride dissolved in water. So you set up you can use this sort of triangle to work it out. So usually you got enthalpy change, calcium chloride dissolves into calcium aqueous and chloride aqueous. Then going down is enthalpy change of the solution, going up is enthalpy change of lattice. So it's formation of this lattice here. So that's enthalpy change of solution, okay, and lattice is the other way around. So if you say that's lattice here, formation lattice, and that's enthalpy change of hydration and hydration. So hydration calcium 2 plus, and then you've got hydration chloride. Sorry. So you start by setting up your equation. So if you say enthalpy change of solution equals 2, so that's enthalpy change of solution equals to enthalpy change of the solution plus enthalpy change of hydration of calcium and hydration of chloride ions. So if you take all the information here, remember if you enthalpy change the solution, this one here is the solution, but that value there is lattice from formation. So you need to change the sign to plus 2237. So the answer will be minus 141 kilojoules per mole minus 1. So then you got 5.2. You got use your answer question 5.1 to deduce how temperature changes when calcium chloride dissolves in water. So the temperature will increase because it's an exothermic reaction. Okay. Explain why the enthalpy change hydration of fluoride ions is more negative than enthalpy change hydration of chloride ions. You all know that fluoride is a smaller ion, so it's got high charge density, so it has a stronger attraction of fluoride ions to the delta H of the water molecules. 5.4, figure 2 shows an incomplete Born-Haber cycle, so you have to complete it. So you start by adding those bits in there. So what are those bits? You need to look at it and say, this is one here is enthalpy change of formation. So if I've said enthalpy change of formation goes down, any arrows go up is positive, and you follow all together when you're adding them up. Any arrows going down is negative. Okay, so that's negative, that's all positive, and that's negative. So it says to complete the Born-Haber cycle by writing the formulas missing species. So it's hold on, let me just check something. See. So what you do, you look at it. So that's formation. That one is the calcium solid goes into gas, so it's atomization of a calcium. So then you have calcium goes up to calcium plus, which is ionization, first ionization of calcium, ionization of calcium, and it's the first one. And then you got the second ionization of calcium here. And then you have, because that stays the same here, can you see it's calcium 2 plus 2 electrons stays the same. The only thing it changes is Cl2 gas goes into 2Cl gas. So that means your chloride ion has been atomized. So that one is enthalpy change of atomization of chloride. And then here is electron affinity, okay, of chloride ions. So if you got chloride ions plus 2 electrons makes 2Cl minus, then you end up with that there. And then this is one is lattice, delta H lattice, okay. So then you have the values here, complete Born-Haber cycle. So you know, so you got calcium solid goes to gas, so you change that. And here you know that calcium chloride gas goes to atoms, so you change it to Cl gas, because there's 2 lots, so you get 2 lots. That's all you have to do for that question. Then you move on to the next bit here, and he says here, table 3 shows some enthalpy change data. So you got all the data here, and he says calculate the second ionization energy of calcium. So the first thing you need to do, you got to remember that you have to do delta, anything goes this way, you add them together. So anything goes that way. that anything goes around, you add them together. So you got that plus that plus that plus that plus that plus that, okay, equals to that. So that one is enthalpy change in formation, which is minus 795 there. Then you add everything up, and you will know that enthalpy change, second ionization energy, is your unknown. You arrange that into to find your unknown, the second ionization energy of calcium, and then you work out that the answer, if you add them all up together, will give you plus 1145. And that's the answer of the question. Here I multiply by 2 because there's 2 lots, okay? And that's the only thing you need to know. And that one you multiply by 2 because there's 2 lots in there. All right? Question 5.6, explain why the second ionization energy of calcium is greater than the first ionization energy of calcium. So your electron is being removed from a positive charge, therefore it's closer to the nucleus. You don't have to say all that, but I'm just trying to explain is one of the answers. Electron is being removed from a positive charge because you already taken one electron, so it's going positive, so it's much closer to the nucleus, so it's much more attraction from the nucleus to that electron you're trying to remove, so therefore it's going to be greater. Then it says here 5.7, table shows lattice enthalpies based on perfect ionic model and lattice enthalpies of Born-Haber cycles 3 metal chlorides here. So you got calcium chloride, potassium chloride, silver chloride. In your answer, you should discuss the values in table. So you have got 6 marks to discuss the values in table 4. In your answer, you should compare the 3 values based on the perfect model ionic model ion. Compare the values based on the perfect ionic model to the values from a Born-Haber cycle each compound. So you need to compare first 3 of perfect ionic ion, and then you compare with each other. So in a perfect ionic model, calcium chloride value is larger than chloride, KCl and HCl. That's correct. Calcium 2 plus has a larger charge, so is a smaller ion. Ag, silver plus and potassium plus has smaller charge, so larger ions. Calcium chloride has a stronger ionic bonds than silver chloride and potassium chloride, which has weaker ionic bonds. So that's the conclusion of that. Then calcium chloride has similar values between the perfect ionic model and Born-Haber cycle, for that one there. Then potassium chloride has similar value between the perfect ionic model and Born-Haber cycle, so they're similar. And then you have as calcium chloride and potassium chloride, calcium chloride and potassium chloride have almost perfect ionic model bonding, because that's the similar values in there, okay? So silver chloride has the largest difference between the values of the perfect ionic model and the Born-Haber cycle. So you're just saying that's the largest difference. Therefore, silver chloride contains some covalent character. Silver plus ion is more polarizing, as it distorts the electron cloud more. So that's why it has more covalent character. Okay, I hope it makes sense. So you're just comparing everything between them to get the 6 marks. Question 6. The concentration of dilute hydrochloric acid can be found titration using standard solution of barium hydroxide. Calculate the mass in grams of solid barium hydroxide, which has got MR of 171.3, needed to prepare 250 centimeters cube of 0.1 mole decimeter cube barium hydroxide solution. So you start by using moles, calculate moles, which is moles equals concentration times volume divided by 1000, because that's centimeters cubed there, gives you moles of barium hydroxide. Moles equals mass over molar mass. So if you replace the values there, so you got, gives you the value of, you got moles 0.025 times the molar mass, and gives you the mass in grams, which is 4.28. The mass barium hydroxide of question 6.1 is dissolved in a beaker containing 150 centimeters of distilled water in a centimeter cube. Describe how the solution is used to make 250 of the 0.1 barium hydroxide. So basically you've got to go through the process of the practical you do in school or college, whatever. First of all, you've got to transfer the solution to a volumetric flask. There's 3 marks. You've got to say 3 different things. Transfer the solution to a volumetric flask. So you actually take in the beaker, you mix the solution, dissolve it completely, put it in a volumetric flask. Then you add washings using distilled water. So that means you add some more water to the beaker, you clean it all, and you transfer all to the volumetric flask, and you make up to the mark graduation 250. Then you take distilled water and you add it to 250 exactly. Okay, so you know exactly what's concentration. The reason you do that is that you don't have anything behind. You don't leave anything behind. Then, third part, invert the volumetric flask many times to ensure that the concentration is in equilibrium. So you got to put your finger on a lid and invert a few times, so you're mixing all together to get the concentration correctly. All the same in everywhere. 6.3. Before first titration, the 25 centimeters pipette is rinsed with a small volume of 0.1 barium hydroxide solution. State-wise, a good practice to rinse the pipette in this way. So the titration is done with non-concentration barium hydroxide. It will not be contaminated with water affecting concentration. So if you actually don't rinse the burette with barium hydroxide, it might have some distilled water there. We should dilute the solution. Your concentration will be not correct when you're doing the titration. So like this, you're not contaminated with water. Hopefully that makes sense. 6.4. Hydrochloric acid is added to the burette using a funnel. State-wise, a good practice to remove the funnel from the burette before the titration. Well, to stop extra drops entering the burette, so this will decrease the titer. So that means if you get extra drops, you got incorrect value going in there, so you think you have the correct concentration, but you actually got more there. So that's the reason. So you need to always take the funnel out of your volumetric flask or burette actually. In a different experiment, 0.9252 grams of sodium barium hydroxide is used to make 250 centimeters of standard barium hydroxide solution. So you put 25 of this barium hydroxide solution, reacts with exactly 24.5 hydrochloric acid. Okay, so you have the equation here, barium hydroxide plus 2Cl, HCl gives you barium chloride plus water. I hope that's balanced, I think it is. So I think you got barium and you got chloride, 2 chlorides, and you got 2 H's there, and you got 2 H makes 4 H. Actually, I don't think it's balanced, but it needs a 2 here. And then you got 2 oxygens there. So you start by calculate concentration hydrochloric acid. So moles of, we don't care about this at the moment, so it doesn't matter. Moles of barium hydroxide, you got 0.952, which is there, mass, divided by molar mass, so you work out the moles of barium hydroxide. So in 250 centimeters cubed, you got 0.00556 times 10, so that's 10 times more because that one is only 25, so you multiply by 10. So moles of HCl in 24.5 is going to be times 2 because the ratio is 1 to 2. So you're going to end up at 0.00111 moles. So then moles equals concentration times volume. So you got moles equals concentration times volume. So you know the volume is 24.5 divided by 1,000. And the valid concentration of the concentration is going to be 0.045. This is the concentration of the hydrochloric acid found out. Okay, 6.6. The uncertainty value of 225 centimeter solution from the pipette is 0.05. The total uncertainty is 24.5 solution from the burette is 0.15. Calculate the total percentage of error in using the burette. So you calculate individual. Remember, if you got pipette, you only have one error. So 0.5 divided by 25 times 100 gives 0.2. And it says the total uncertainty of that, so because the errors are added together, because there's 2 errors, but it says the total uncertainty in 24.5, so you don't have to multiply by 2 there. So it'd be 0.15 divided by 24.5 times 100 gives you 0.612. So if you add them together, it gives you 0.81%. I hope that makes sense for you.